Here we're continuing exercise 1930. We're starting with benzene, and we want to synthesize this molecule from benzene. The first step is just to think of what recipes you need to use. And we have our little recipe summary over here for this chapter, and the last one. And so here, if you want to put a bromine on a benzene ring, you have to do bromination, and that is where you add Br2, and you could add either AlBr3 or FeBr3. So I'm going to write down the Br2 and also the FeBr3 because that's the catalyst we used in the mechanism earlier in this chapter. But AlBr3 would work just as well. So that's the first thing. To put this other group on here, it's a little tricky. We know we're making a new carbon-to-carbon bond, but this has those 3 bromines. That actually has to be done in 2 steps. In the first step, you can use the Friedel-Crafts alkylation to put the carbon on. In the second step, you now have a benzylic position, and you can use excess N-bromosuccinimide with heat, NBS with heat, to add bromines to replace those hydrogens there. So it's sort of a 2-step process. In the first step, you would add the CH3Cl, that's your alkyl chloride, your alkyl halide, and then AlCl3. So that would put this carbon on this ring. You'd have CH3 there after that. And then once you have that benzylic position, and you can use excess NBS and heat. And that replaces the 3 H's with 3 bromines. So those are the recipes you need to use, but then you have to think about the order you need to use them in. We have here, our branches are meta to each other. They're 1, 3 away from each other. Bromine is weak. This branch, bromine branch, is a weak deactivator, and it is ortho-para-directing. CBr3, that's like CX3. That's one of the 3 strong deactivators. And like all the strong deactivators, that is meta-directing. So we have to do these reactions first, because that leaves us with a meta-directing branch. If we have that first, then the bromine will add meta. If we put the bromine on first, then this other branch would add ortho and para, which we don't want. So we have to add that CBr3 first. So we'll take benzene, and first step, we'll do the Friedel-Crafts alkylation. We don't have to worry about carbocation rearrangements. We'll form this methyl carbocation, but it won't have any other carbon to rearrange to. So that'll give us CH3 here. Now we can use excess NBS with heat, and that replaces those hydrogens with bromines. So we have bromines. We saw how you could use just one equivalent of NBS with heat to put a bromine on the benzylic position. Here, if you use excess, you put as many bromines as you possibly can. So now we have that CX3, which is a meta-director. So now we can add the bromine, Br2, FeBr3, and the bromine will add only on the meta position. And so we end up getting the product that we want. So this whole synthesis is how you can make that product. The steps are first figure out what recipes you need to use, and then based on the orientation of the branches, ortho, meta, or para, think about the order you have to do those reactions in. Okay, so that's E. Let's try F. So first, let's just think about the recipes we need to use, and actually this is the same as the last one, right? Bromine and CBr3. Same two branches, so we'll use the same recipes. To add bromine, you use Br2, FeBr3. To add this CBr3, first do a Friedel-Crafts alkylation, so CH3Cl, AlCl3. Once you have that methyl group on there, replace the hydrogens with bromines by using NBS, and here, because we have 3 bromines, we'll use excess. This just means same, it's an abbreviation for excess. So excess NBS with heat. So those are our 2 recipes, but this is different from the last one because in this example, these branches are para to each other, sorry. They're para to each other. In the last example, they were meta. Now they're para. And so even though we use the same recipes, we're going to have to do them in a different order. We saw how the bromine is a weak deactivator and how it's orthopara directing. We also saw how the CBr3 is a strong deactivator and how it's meta-directing. Well, we want the para product, so we have to put the bromine on first. Now you could actually do this one other way. You could add the methyl group, that's an alkyl group which is orthopara directing, and then you could add the bromine, and then you can add the NBS. But for simplicity's sake, we'll just work with the bromine, which we know is orthopara directing. So we have benzene, add the bromine, that bromine is orthopara directing. So when we do this next Friedel-Crafts alkylation, we will end up getting 2 products. We'll get the ortho product, but we'll also get the para product. And it's the para product that we'll use. So we take that para product and we treat it with excess NBS and heat that turns the 3 H's into 3 bromines on that benzylic position. And so we end up with exactly the product that we wanted. And so you can get that para product just by doing those same reactions in a different order. Right? The same reactions that we did in the previous example, we just did them in a different order, and instead of getting the meta product, we get the para product. So that illustrates the importance of the order of doing the order in which you do these reactions. All right, let's think about G. Now in G, we have 2 branches. Each of these branches are alkyl groups. And so how would we put alkyl groups on there? Well, some sort of Friedel-Crafts reaction. It'll either be Friedel-Crafts alkylation or Friedel-Crafts acylation. Let's think about them one at a time. If we're just putting a CH3 on the benzene ring, then we could do Friedel-Crafts alkylation. You could take that CH3, instead of going to benzene, have it going to a chlorine, and then AlCl3. And the reason why you can just do regular old Friedel-Crafts alkylation is because you end up forming the CH3 intermediate that has a positive charge. You end up forming that Austen electrophile. And there's no way that that carbocation can rearrange. So that's perfectly fine. The benzene ring will attack that carbon. you'll get the product you want. But what would happen if you tried to do a Friedel-Crafts alkylation with this branch at the top? You would take that branch, instead of attaching it to benzene, you would have it attach to a chlorine. And in the process of the reaction, as you know from the mechanism, the chlorine would go and you'd end up having that carbocation there when the chlorine goes onto the AlCl3 catalyst. But that carbocation is primary. This carbon is only bonded to one other carbon. Right next door, if it moved next door, it would be tertiary, which is more stable. And so if you did a Friedel-Crafts alkylation, you would get this carbocation rearrangement. And then the nucleophile would attack that middle carbon, and you would end up with the benzene ring attaching there, this tertiary carbon, so you get a tert-butyl group rather than this isobutyl group. So you can't use a Friedel-Crafts alkylation here because you would get a carbocation intermediate and it would give you a different product. You would get a carbocation rearrangement and you'd get a different product. So instead, the workaround is we can do Friedel-Crafts acylation and just reduce it. That avoids the carbocation rearrangement. So we can do this by taking that same group. Instead of the bond to the benzene, though, we'll have a bond to a chlorine, but otherwise the same group. But we just have to put that acyl group there, because this way when we form the carbocation, it'll be stabilized by the acylium ion that we saw in the mechanism, and it won't rearrange. So we'll take that, combine that with AlCl3. That would give us this product with this with that acyl group, and then we just have to reduce that. So we would reduce it with that zinc mercury amalgam with HCl and heat. Okay, so those are our recipes. Those are the ingredients we're going to have to use. Now let's think about the order we need to use them in. This group at the bottom is weakly activating and orthoparadirecting. The group at the top is an alkyl group. It's weakly activating and orthoparadirecting. So technically, we could do them in either order, technically. So either order would be counted correct on the test. But ideally, you would want to, okay, so either order is fine. Okay, so we'd take benzene, our benzene ring here, and then we could, take benzene, and then we'll do our Friedel-Crafts, let's say the Friedel-Crafts acylation. So we have this that first step, and then we can reduce that with a zinc mercury amalgam and HCl and heat, and that gets rid of those bonds to oxygen, replaces them with bonds to hydrogen. And then last, we just need to put on the methyl group, and so we can do that Friedel-Crafts alkylation. And we'll end up getting two products there, the ortho and the para product. So the ortho product is the product we want, the para product not so much. But we do get the product we want, and then we can just separate it through distillation or chromatography. And so this synthesis is a synthesis for how you can make that molecule from benzene. Okay, I'm going to do H, I, and J in another video just to avoid making